of a type of observation, right? So measuring, for instance, the length or the width of this table, right, using a particular device and reporting that, that would be an observation about the length of the table. And we make measurements all the time in chemistry. All right, so measurements are examples of observations. Or if you want to be a little more technical, data that you can collect. All right, in chemistry and in science in general, we are going to use the metric system. All right, so you know, growing up, you know, you probably are familiar with not the metric system. All right, so inches and feet and yard and Fahrenheit and pounds and ounces. We're not going to touch those in chemistry. We're going to use a metric system because it's a standard system. It makes sense. The entire world uses it, with the exception of us. So the metric system has been around for a long time. There's an adaptation of the metric system called the SI system that we're going to see as well. There's some similarities between them. SI, anybody know what SI stands for? So it stands for the International System. Right, and you may think, well, why isn't it called the IS system? Well, it's actually based on the French name, which is Système International. So that's where the SI actually comes from. And it's just an adaptation of the metric system. Okay, so we're gonna introduce this system of measurement, and we're gonna use it throughout this entire class. You're gonna see it also when you get to your anatomy, your physiology, your microbiology, and if you take other science classes as well, you will deal strictly with the metric system. All right, so there are several things, several dimensions, several properties, several characteristics of different things that we can measure. And there are units that we use, base units that we use in both the metric and the SI system. And there are abbreviations that we use, again, to sort of shorten or as shortcuts for those units. I'm going to put a big star by this table, or several stars by the... Why do you think I'm putting 4 stars on that table? You need to know those. You need to know the units as well as their abbreviations.
I can't pull up 2.1. Yeah, it's not.
I'm sorry?
2.1 isn't pulling up on the link.
It isn't? Okay, so technical issues, I guess we'll just have to, take regular notes at this point, and I can't address that right now. I'll have to wait till I get back to my office to troubleshoot that. But everything that is on the PowerPoints, these are taken directly from your textbook, by the way. So all of the tables and all the diagrams and stuff from the text, right? And they should be labeled, yeah. So table 2.1 would be the first table from your textbook. So if you have your laptop out, you can bring up the e-text, and you can see the table. All right. So several properties or several characteristics that we can measure. The first is volume. In the metric system, we use the liter, and liter has the abbreviation uppercase L, big L. It may not seem like a big deal to you at this point, but it will become a big deal if you are one of those people that like to write everything in capital letters. Big problem in chemistry, big problem in science. Right? Uppercase versus lowercase, they can have very different meanings. All right, we'll see some examples of these down the road. All right, so liter, metric system for volume, big L. For the SI system, we use the cubic meter, which is small m, raised to the power of 3. And volume is a very common thing that we measure. We're going to have some practice with that today. those of you on Monday measured some volumes as well in the laboratory. Length, in both the metric and the SI system, we use the meter. And the meter has the abbreviation small m, lowercase m. For mass, in the metric system, we use gram, which has the symbol small g. In the SI system, we use kilogram, which has a symbol small k, small g. For temperature, we use degrees Celsius in the metric system. We use Kelvin. Somebody heard Kelvin before for temperature? Right? It's one. If you haven't taken a science class before, right, you probably would never have heard of Kelvin. But it's the temperature that we use strictly in chemistry, especially when we get down to gases. And start looking at some of those calculations. Kelvin has the symbol big K. And then finally, time, we use seconds for both of these units, the metric and the SI system. Right? So you don't see, for instance, volume, you don't see pints and quarts or ounces. For length, you don't see inches or feet or mile. For mass, you don't see pounds. For temperature, you don't see degrees Fahrenheit, which is probably what you're most familiar with. All right, so the metric system, SI system, we're going to use these units as sort of jumping off points for other units that we're going to see down the road. All right, so the quicker you familiarize yourself with these units, the better your life is going to be in this class. All right, let's take a quick look at each of those things and a description of what they represent. So the volume can be described as, the volume of something is simply the, something has a volume. So this trash can here has a certain volume, right? This pen has a volume. What would you describe the volume as? Sorry? Liters. So that's a unit, but if you had to describe volume, the amount of space that something occupies. All right, we saw in the previous table that we use cubic meters in the SI system. In the metric system, we use liters. And in the laboratory, right, we're generally going to use liters as our measuring system for volume. But more commonly, we're going to use a smaller unit called milliliters, which has the abbreviation small m, big L. Right? 24 of you, right, should be a little more familiar with that because you did that on Monday in the laboratory. All right, so volume, the amount of space occupied by something. We typically use milliliters in the lab. Just to give you an idea of what the metric unit corresponds to in terms of something that you may be familiar with, right? So a liter is about equal to a quart. There's not an exact relationship, but they're about equal to each other, right? So when you go, when you buy milk, for instance, at the grocery store, right, it comes in a couple different sizes, right? Is it sold by the liter or is it sold by a different unit, milk? It's sold by the gallon. And it's also sold by the quart, which is smaller than a gallon. How much of a gallon is a quart? What does quart sound like? A quarter, yeah. So a quarter or a quart is a quarter of a gallon. Right? And a quart is about 1 liter, roughly. So how many liters, roughly, do you think there's in a gallon? Around 4 liters. Right? A little bit less than 4 liters. When you buy a gallon of milk, right, whether it's the good stuff, the whole milk, or the other things, if you look right below the lid, it'll actually tell you 3 point something liters on it. All right, length, the dimensions, how long something is or how wide something is. We use the meter in both the metric and the SI system. And again, meter has the abbreviation small m. In the laboratory, when we start making measurements, we really don't have anything that big to be measured in meters. So we usually use centimeters as our unit, or sometimes millimeters. And centimeters has the abbreviation small c, small m. We will talk about these other abbreviations here down the road, so don't feel like you have to know them right away. In terms of what the metric unit of length corresponds to, in terms of what you may be familiar with, right? A meter is roughly equal to a yard, right? So if you know a yard is about that big, that's roughly equal to a meter. Not exactly the same, but it's approximately the same. An inch, well, that big is just over 2.5 centimeters, right? Just to give you an idea of how these metric units correspond to units that you may be more familiar with. Mass, so we can define the mass of an object as a measure of the amount of matter in it. Right, how much stuff is in that thing. We typically use a balance in the laboratory. This is what a balance looks like, and this actually looks very similar to the one that we have. We mentioned the SI unit for mass is kilogram. But in the laboratory, we don't deal with huge amounts. We deal with smaller amounts of things. And the units that we're going to see more frequently would be gram, which has a symbol small g, and milligrams, which is small m, small g. Right? Those are the most common units for mass that we'll encounter, especially in the laboratory, with tiny amounts of things. In terms of what the metric unit corresponds to, a kilogram, which is the SI unit of mass, is just over 2 pounds, right? So if you can think about what a pound or a couple pounds are equal to, that's roughly equal to a kilogram. Right? A lot of these metric, again, you may not have seen, metric units before, and it takes a while to wrap your mind around it. But once you get into the swing of how the metric system works, it's actually way easier to use than the English system or the imperial system. All right, temperature, a measure of how hot or how cold something is. And there are a couple of reference points that we use for temperature scales. The boiling point and the freezing point of water, right? So you may be familiar with water freezing at 32 Fahrenheit, 32 degrees Fahrenheit. That corresponds to 0 degrees Celsius. And then water boils at 212 degrees Fahrenheit, which corresponds to 100 degrees Celsius. We're going to start using the Kelvin scale. And when we represent the temperature in Kelvin, we just say Kelvin. We don't say degrees Kelvin. There's no such thing as degree Kelvin. So for instance, this 100 degrees Celsius is equal to 373 Kelvin. There's no degree Kelvin, it's just Kelvin. Kelvin is also called the thermodynamic temperature. All right, we're going to use that, like I said, when we get to gases and stuff down the road. On the Kelvin scale, there is a 0 point in the Kelvin scale. So 0 Kelvin is known as absolute 0. Right? And that's the coldest temperature possible. Really, really, really cold. Extremely cold. So cold, in fact, that nothing moves. Right? Even the tiny motions within particles, they just stop altogether. All right, and then the last one we talked about was time. And there's several different devices that we can use to measure time, stopwatches, etc. The unit that we use here is seconds in both the metric and the SI system. Second has the abbreviation small s. All right, so those are the units that we're going to use in the metric system to represent different things that we're measuring, you know, whether it's time or whether it's temperature, whether it's volume, whether it's mass, whether it's length. So let's recap really quickly. I'm going to jump down here to this one. And I know we just talked about this. I'm going to test your short-term memory. All right, what's the SI unit? For, let's start with D, temperature. SI unit for temperature is Kelvin. Abbreviation for Kelvin? Small k, big K? Big K. SI unit for length, the meter. Abbreviation, small m. SI unit for mass, kilogram. And the abbreviation is small k, small g. And then volume for SI is, we'll just put cubic meter. So whenever you make a measurement of anything, there should be two components to that measurement. There should be a number, and there should be a unit that tells you what it is that you're measuring, right? So if you measure the length of a table and you say it's 1.5, okay, and you report that on a, you know, on an exam or a quiz, right? I'm going to draw a little frowny face on it and some question marks. 1.5 what? 1.5 oranges, 1.5 puppies. What's your unit of measurement that you're using? Right? So the unit of length, right? The metric unit of length would be meters. So you always want to keep that in mind. Whenever you make a measurement, you have to have two things, a number and the unit that goes with it. They go hand in hand, like milk and cookies, or peas and carrots, or peanut butter and tuna fish, or whatever your favorite combination is. All right. So that's a brief introduction to the measuring system, the metric system, and the SI system. Let's jump to how we treat measurements. In other words, how we deal with those actual numbers that we get from making these measurements. So whenever we make measurements, we're going to depend on a device or an instrument to make that measurement. And that device or that instrument is going to have graduation marks on it or increments on it that are going to guide us in terms of how we're going to accurately portray that dimension or that thing that we're measuring. All right, so the tool or the device that we're using is going to dictate a lot about what our measurement is going to look like. The tool that we're using is going to provide our numbers for whatever that measurement is, and we're going to call those numbers measured numbers. All right, so for example, we have here, you know, a ruler. It's calibrated in centimeters, and we can use that ruler to measure the length of that piece of wood, whatever we decide that to be based on our instrument. So we'll first of all take a look at how we report length, and we're going to apply this to measuring other things like volumes, etc. The key thing that you want to keep in mind when it comes to making measurements is that you are at the mercy of your measuring device. Right? And again, half of you saw this on Monday. The increment, the smallest increment in your measuring device dictates how precise you can be with your measurement. So you really have to pay attention to what the tick marks tell you, because you want to accurately convey that information without making up data, but also not selling your instrument short in terms of what it actually is guiding you to do. All right, so we're going to decide, first of all, when we make a measurement, what's the smallest increment, right? An increment, again, a fancy word that just means the amount between the smallest or the closest tick marks or graduations on your device. All right, so we'll bring back this ruler into play, and then we have our piece of wood. What's the smallest increment on that ruler? In other words, what's the distance between the closest tick marks? Between 3 and 4, between 3 and 2, between 2 and... It's 1, right? The smallest increment is 1 centimeter. So if I were to measure the length of this ruler, okay, we can say with absolute certainty that it's more than 4 centimeters, but it's less than 5. Do you agree with that statement? It's more than 4, but it's less than 5. Right, it happens to fall right here on our ruler. So we are absolutely certain that it's 4 point something. It's somewhere between 4 and 5. So you, as a person making this measurement, get to estimate how much between 4 and 5 that piece of wood is. And what would you say? It's halfway between 4 and 5. Okay, so if halfway between 4 and 5 would be 0.5. Okay, so 4.5 centimeters. Anybody think that it could be something different? Well, if I look at it from this angle, it looks like it's a little bit less than halfway. I actually think it's 4.4 centimeters. Right? So both of our measurements are similar in the fact that we both have, we're saying that it's 4 point something. The way that it's different is in that second digit there that we're estimating. Right? So this here is our estimated or uncertain digit, right? And in this case, it's which place is that? The 100th, the 1000th, the 10th place, right? And we can estimate to the 10th place based on the fact that our smallest increment is 1 centimeter. So we can represent that uncertainty as plus or minus 0.1 centimeters, the 10th place. Right? So again, you think it's 4.5, I think it's 4.4, somebody else may think it's 4.6, again from a different angle. So the last digit in any measurement is going to be estimated or uncertain. If you're making that measurement with your eyes, you have to decide, based on what you see and what the smallest increment is, what that uncertainty or what that last digit is. So your ruler in this case dictates how you can make that measurement. Let's say that we tried to measure the length of that ruler using the length of the piece of wood using a different ruler. I'm going to zoom in here a little bit. What's the smallest increment on this ruler? In other words, what's the distance between the closest tick marks? 0.1? Can we vote? Do we agree with 0.1? Raise your hand if you think it's 0.1. Is it still 1? You think it's still 1 as the smallest increment. Okay, great. It's not 1, right? Because 1 would be this, but we have smaller graduation marks between them. And between each of these main, the 1s and the 2s, we actually have 10 equal divisions, right? So each of those small spaces, each of those increments then would represent 1 centimeter. Right? So the smallest increment here is 0.1 centimeter. So for example, this is 1, that's 1.1, 1.2, 1.3, 1.4, 5, 6, 7, 8, 9, 2, 0.0, 2.1, etc. So now, with the same exact ruler, or same piece of wood, what would you report as the length of that piece of wood? Zoom in even more. I'm going to erase this because it's not, I don't want to tell you what. Zoom in even more. So we're saying each increment is 0.1, right? So this, what would this be? 4.1, 4.2, 4.3, 4.4, 4.5, and 4.6. So it's 4. So we can say then, without any argument from anybody, that that piece of wood is more than 4.4, but I'm sorry, more than 4.5, but it's less than 4.6. Do you agree with that? Yes. All right. So we know then that it is 4.5 something. It's somewhere between 4.5 and 4.6. And if it looks like it's exactly in the middle, right, we can say that it's 4.55 centimeters. Again, somebody else may think, well, it's a little bit less than that. Maybe it's 4.54 or 4.56. They all differ in that last digit, which now is not the 10th place, it's the 100th place. So our uncertainty then is in the second decimal place, which is the 100th place. Let's try this again. Okay, more technical issues. Okay, so our uncertainty is in that second decimal place, so we can say it's plus or minus what? 0.01, right? It's the 2 places after the decimal point, which is the 100th place. All right, so somebody, again, looking at this may think it's 4.56 or 4.54. The last digit there is our uncertain digit. Now you need to include that in your measurement because the instrument dictates that level of uncertainty, right? And you want to accurately portray that or convey that to the person looking at your measurement. Does that make sense? Okay, so I know some of you that had the lab on Monday when we went through the exercise, it kind of seemed a little challenging or confusing. Maybe it makes a little bit more sense now, kind of. Okay, so the people that have lab today, you have a little preview of what you'll be seeing. All right. So if we have a piece of wood now that is this length, if we were to record the length of it using this ruler, what would you say the length of that piece of wood is? 3 centimeters? Well, what's the uncertainty in that ruler? Do you remember? It was 0.1, right? So you can actually estimate to the 10th place. So if you use that ruler and you think that that piece of wood is exactly on 3, it actually has to be what? 3.0, right? Because that ruler dictates that you can estimate to the 10th place. Similarly, if I had a piece of wood and I used this ruler and it happened to be exactly on 3, how would I report that length? 3.00, right? Because that ruler has a smaller increment. Right? So the tick marks, the graduation marks, whatever you want to call it, the increments, they dictate how certain or uncertain you can be in your measurement. All right, let's take a quick look at this one. So we have this red line, assume that it starts at 0, and we have this particular ruler here. How would you report the length of that red line? 1, 2, or 3? So raise your hand with your choice. So either 1 finger, 2 fingers, or 3 fingers. No other option. Okay. All right. So I'm seeing mostly one answer, but a couple of the other ones, some people change their answers. All right. So what's the smallest increment here in our ruler? So that's 9, and that's 10.
0.1.
So the smallest increment is 0.1, right? Which means you can estimate to 1 more decimal place. So 3. I'm sorry, option 3. Which would have 2 decimal places, right? It falls exactly here on 9.2. That's just like the ruler that we looked at previously. We can apply that technique to rulers. We can also apply the same technique to other devices that measure volumes, for instance. The calibration is going to be, or the increments is going to be the exact same thing. Right? Instead of being horizontal, though, they just go vertical. You're using the same technique when it comes to measuring volume in a graduated cylinder, etc. All right. Questions on that? Questions on making measurements based on the instrument that you have? Okay, so we're going to jump into, in the remaining time that we have about 9 minutes. Or do we? What time do we end? 11:15 or 11:10? 11:15? Okay. So we're going to take a look now at how the measurements that we make affect what we do to those numbers. For instance, if we have to use them in calculations. So every number that you get from a measurement is going to affect the number of what we call significant figures that we have. So significant figures, which are often abbreviated as sig figs, or just SF, are going to be important when we deal with measurements. Right? They're extremely important when it comes to making measurements. We're going to include all of the digits with our sig figs, including whatever digit it is that we're estimating, that very last digit in our measurement. Has anybody heard about sig figs before? Does it conjure up pleasant memories or not so pleasant memories? Sig figs. So sig fig can be a little confusing. All right, so we're going to try to slow it down a little bit and break it down into some basic rules for identifying and then counting, determining how many sig figs we have in a particular measurement. So there are several rules. The rules are as follows. Any digit that is a non-zero digit is always significant. So non-zero would mean 1, 2, 3, 4, 5, 6, 7, 8, 9. So for instance, 253 centimeters would have how many sig figs? 3 sig figs. Right? All of those digits are significant. So the rule governing non-zero digits is pretty simple, right? They're always significant, no exceptions. The problem arises with the zeros, right? That's where all sorts of issues come up and people get confused. So let's try to address that right now. So zeros. Are significant. If they are trapped or sandwiched between non-zero digits. So for example, 405 meters, right? Obviously, the 4 is significant because it's non-zero. The 5 is significant because it's a non-zero digit. And now the 0 here is trapped between these two non-zero. So this 0 is significant. All right? So this number then would have how many sig figs? 3 sig figs. Right? You can have trapped zeros throughout a number. It doesn't just have to be in the middle. So for instance, we can have 1, 0, 5, 0, 2, 1. Let's see, that's meters as well. How many sig figs in that one? All of the digits are going to be significant, right? Because all of these zeros are trapped. So 1, 2, 3, 4, 5, 7 sig figs in that number. Right? So trapped zeros, sandwich zeros, we can also call them, are significant. Zeros are also significant if they are at the end of a number with a decimal point. So if there's a decimal point in the number, and there's a 0 at the end, or zeros at the end of the number, those zeros are significant. All right, so for instance, if we have 1.0, right, the 0 is at the end of that number. Does the number have a decimal point? Yes. So this then would have 2 significant figures. Okay, if I have 100.0, how many sig figs in that one? Okay, so obviously the 1 is, right? And we have some zeros. Where are they in this number? They're at the end. Does the number have a decimal point? Yes. So are the zeros significant? Yes. So how many sig figs do we have? 4 sig figs. Right, what this is telling you is that when you made this measurement, whatever this measurement was, you could estimate to the 10th place. That's why you include it in the measurement. All right, so as long as there's a decimal point in the number, the zeros at the end are always going to be significant. They don't have to be after the decimal point, right? They can be before the decimal point as well, as long as they're at the trailing end. So those are called trailing zeros. Yes?
What if it's 100?
We'll get to that. So the presence of the decimal point makes a huge difference, or it's a big deal. All right, so that's if zeros, the instances when they can be significant. What about when they're not significant? I'll do this in a different color. I'm running out of room. Let's see. So zeros are not significant if they are at the front of a number. And we call those zeros leading zeros, because they lead into the actual non-zero digit. So for instance, if I have 0.002, all right, so we have zeros, they're at the front of the number. Significant or not significant? According to this rule, they're not significant, right? They're not at the end of this number. They're at the front. And the fronting or the leading zeros are never significant. So this is 1 sig fig. Just the 2 is significant. What if I change that up a little bit? And let's say I had 0.0020. How many sig figs now? Is it still 1? 2 sig figs, right? So we already established that these zeros here are not significant because they're leading zeros. All they do is they determine the size of the number. The 2 is significant, and then the 0 at the end now, it's a trailing 0, and the number does have a decimal point. Right? So that 0 at the end is going to be significant. So this will have 2 sig figs, right? Both of these here will be significant. So leading zeros, not significant. The other instance where the zeros are not significant is if you have the zeros at the end of a number and that number does not have a decimal point. All right, so for example, if I had 100, right, so obviously the 1 is, now I have these trailing zeros, they're at the end of this number. There's no decimal point in the number. There's no explicit decimal point. So these zeros then are considered not significant. All right, so that would have 1 sig fig. If I have 1010, 1010, how many sig figs in this one? 3, right? The other one is, this trap 0, always significant. So 1, 2, 3, the 0 at the end of a number without a decimal, not significant. So that's going to have 3 sig figs. All right, so as we've gone through the rules, right, hopefully you've seen that the issue lies with the zeros, and the presence or absence of the decimal point makes a difference, specifically if you have trailing zeros. Trapped zeros in the middle of numbers, always significant. Leading zeros, never significant. The zeros at the end is where the problem is. And you just look to see whether there's a decimal point or not.